we're going to open the submission link for the next problem set tonight, but it's not due until Friday, okay? All right, guys, homework's going to be due on Friday, okay? That's what we were just talking about. Okay, cool. So I'm going to give a lecture today. I'm going to do all board work. It's going to match the slides and the book like pretty closely. I might add a little bit here and there. So the slides will still be useful. You can use them for reference. I'm just going to be filling in some of the blanks and hopefully maybe some common points of confusion. So the whole point of what we're going to be doing today for the next couple of lectures is to get at the entropy, okay? And we talked about this early on in the course, this equation called the Boltzmann relation, Boltzmann crowning achievement. It's on his tombstone in Vienna, okay? Do you guys recall what this omega is? Do you guys remember what it is? Jesse, you're nodding your head.
The number of microstates?
Yeah, the total number of microstates, okay. And then the way we might express this is, the way we do this in the book and in the slides, is you write it as the sum over nj of w of nj, okay? So what this w of nj is, this thing is the multiplicity of the macrostate associated with the distribution nj, okay? And then we sum over all possible distributions, and we get that's how we arrive at omega, right? And so like, what do we mean by this distribution nj? And this was something that really confused me when I took the course. So we've been talking about energy levels and degenerate like number of states and energy levels, okay? But what we really mean for all the analysis up until we get to our final like Boltzmann is we've partitioned the energy axis, okay, into a bunch of different bins or energy groups, okay? And so it's like you have like a bin 1, 2, and they all have width d epsilon, okay? And the states, especially when you're at a high enough temperature, the states are extremely dense. So you have a lot of possible states in this bin. Let's say j is here. You have j plus 1. And then we label this like some energy in the middle, we'll just call it the energy in the middle, we'll call it epsilon j. Okay, so what nj is it's the number of particles in the interval j times d epsilon times 2j plus 1 times d epsilon. Okay, so it's exactly kind of like the type of thing we mean when we say we have a distribution over velocities, right? We're talking like the distribution function is telling you what proportion of the particles are from like c to c plus dc, right? So it's the same idea. That's why we call this nj object a distribution. Okay, so keep this in mind. Like, there's the cj is the number of states in this bin. They don't all necessarily have the exact same energy associated with them. Okay, when we're developing the statistics going forward in this lecture. So just remember that. So like cj is the number of particles in this bin, I'll just call it bin j or group j. Okay, so later we're going to talk about a thing called occupation number, and there's going to be some funny business. There's a slide where we just like we switch from an index of j to an index of I, and it's really confusing if you don't understand the fact that we're talking about energy bins or energy groups with multiple states in them. There might be degenerate states in this group, but they don't all necessarily have the same energy. Okay? Okay. So there's another point of confusion. So this thing that we have, this W of nj, that is calculated in the following way. We take the product over the j states in that energy group of W, and then in the slides, it's written this way, ij, okay? And I think Timon might have talked about this on Monday in the tutorial, but for those of you who weren't there, this j in the slides, this j and this j are not the same thing, okay? So this expression in the slide is a little confusing. So let's instead write like WQR. The WQR, which is like this object. What this is the number of ways you can arrange R particles in Q states. Okay, so like in all of our notation going forward, R is the same as NJ, and then Q is the same as CJ. So I would prefer, instead of writing something like this, let's just say it's the sum over J of W, CJ, NJ, just to avoid confusion, okay? So we're going to be working with these objects here. So like I said, and the other thing that we mentioned earlier in the class and we kind of showed through more like a brute force calculation, this thing is essentially equal to the macro state with the largest multiplicity of the distribution that gives rise to that. We'll just call that NJ star. Okay. So we don't have to sum over all the possible distributions because this macro state dominates so greatly that we only are concerned with this. So what we're going to do today is we're going to find that distribution that maximizes the multiplicity of the macro state, and then that will be the distribution that dominates, and we'll go from there. Then we'll be able to derive some thermodynamic quantities, basically get back to the entropy. Because we want to, what we're doing here is we're like enumerating states just using basic statistics, okay? And we're going to arrive at the entropy of thermodynamic quantity, and we can relate that to things like the pressure and the temperature and so on and so forth, right? Through the thermodynamics that we already know. Okay? So that's all just clarification. I think like that's stuff that really hung me up a little bit when I took the course. So let's talk about this expression here, okay? Because this is different for fermions and bosons. Because remember, we talked about the fact that fermions, they cannot share quantum numbers, or they can't have the same state, okay? And then bosons, there's no maximal occupation of a given state. So let's take a couple of minutes to explain how you arrive at this formula. Say, like if we're writing for Fermi-Dirac statistics, we have CJ factorial over NJ factorial times CJ minus NJ factorial. So this is the same as like CJ, choose NJ. How many of you are familiar with this notation? Choose. Okay, so you guys have had like a course of probability or something, right? Okay, so a lot of people may have not had that course. Now, if you know what this notation means, and this is pretty simple. You have CJ bins, and you're trying to choose NJ of those bins to have a particle that occupies them, because you can't have two particles in the same bin. So that's like the quick explanation of why this formula is the way it is. The more simple explanation that doesn't rely on some knowledge of probability is imagine you have CJ states or bins, okay, and you want to go about placing the particles in each way. You want to know how many ways you can do this. And the first particle you place, you have CJ choices. And the second particle you place, you have CJ minus one choices. Okay, you're multiplying these together to get the total number of choices you have. So the first one you have CJ, and then CJ minus one, and so on, until the last particle you place, you have CJ minus NJ plus one choices, the last particle you choose. So this thing that I just wrote down is the same as CJ factorial over CJ minus NJ factorial, right? So you can see that. Now we're still missing the extra NJ on the bottom. Does anybody know where that comes from?
The particles are not distinguishable.
Yeah, exactly. Particles are indistinguishable. So you can permute those particles NJ factorial ways. So we've overcounted by a factor of NJ factorial. So that's how you justify this expression here. for Bose-Einstein statistics, it's a little bit more complicated. Okay, we have nj plus cj minus 1 factorial over nj factorial cj minus 1 factorial. Okay, and this, in that choose notation, is nj plus cj minus 1, choose nj, or choose cj minus 1. Okay, so this one is a little bit more complicated to think about, but instead of thinking about betas, because at this point now you can place all of your particles in a single state. There's no maximum occupation number. So a better way to think about this is you're actually trying to place objects which are particles and partitions between groups, and you have a set amount of positions for those particles, for those objects. Okay, so you have n particles, nj particles, I should say. Then you have cj minus 1 partitions, so like the walls in these bins, cj minus 1 partitions. Okay, and you just need to choose, so that gives you nj plus cj minus 1 objects, okay, or positions in a line, and you're just trying to choose what object you place in each position. So like, for example, if like nj and cj are both 4, and you have like this state here, which is like, let's say it looks like this. You have 2 particles here, nothing, or sorry, then 2 particles like this. So really what this is you have this, if you denote this in like just, you have 7 positions. You could write this as particle, particle, partition, partition, particle, partition, particle. You see what's going on there? The idea? And so really, you're looking at each of those locations and you're thinking, okay, I'm going to take a particle and put it there, and there, put a partition there. And so you can see that when you start out, you have nj plus cj minus 1 choices to make, and then you go down the line until all positions are filled. So you have, the number of ways you can do that is nj plus cj minus 1 factorial. Okay, so like this, I'll just do an arrow there so you can see the idea. And then the particles are indistinguishable, and the partitions are indistinguishable. So you've overcounted by both the number of particles factorial and the number of partitions factorial. Okay, so you have to divide by both of those factors to get the right enumeration. Okay, and then like in the sort of choose notation, it's sort of simple because by the time you've chosen the location of the nj particles, you're already set. You just put the partitions in all the empty spaces. So you only have to choose nj for the specific configuration is determined. So then you have that sort of justification for that formula as well. Okay. So we can go back to the point here. So we're going to use these 2 formulas to derive the distribution that gives us the maximum multiplicity. So we know that this multiplicity of this macro state associated with nj is a product over these w, cj, nj's. And so if we maximize this value, this term, then we'll end up with the distribution that we want that maximizes the multiplicity of that particular macro state. And so the way we'll do this is by using the method of Lagrange multipliers. So the basic setup for Lagrange multipliers is this. You want to maximize some function of some set of variables xi, subject to k constraints. We'll just say like a capital K. K constraints of the form g sub k, so it's little k, of xi is equal to 0. Okay? And then we define this function, this objective. In the slides, it's defined by s, I think that's a little complicated or a little confusing because it's not the entropy, not related to the entropy in any way. And then also, this is not Lagrangian either. I'll just use L for this case. You define this function f of xi plus the sum over all k, lambda k times g of k of xi. So you sum over all the different constraints, and then you attach these lambdas as constants that are called Lagrange multipliers. Okay? And then you take the gradient of that objective with respect to all the xi and the Lagrange multipliers lambda k, and you set that equal to 0. Now, the gradient with respect to the Lagrange multipliers, that's just going to have you're just going to recover the constraints. Because if you differentiate this function with respect to each of the Lagrange multipliers, you just get that specific constraint is equal to 0. So you just recover the constraints. So those are super important, but you just take a gradient and you set it equal to 0. Okay? And so we want to use this method to obtain the distribution that maximizes the multiplicity of its associated macro state. Okay? And at this point, we'll also acknowledge that since the logarithm is a monotonically increasing function, what we mean by that is that if you have x1 is greater than or equal to x2, that implies that like the natural log of x1 is greater than or equal to the natural log of x2. So this is a fact. So because of this fact, instead of working with this thing, which is a product of those, we can take a natural log of that and then maximize it instead. Okay, and that allows us to turn this product into a sum, right? Because the natural log of the product is the sum of the log of each of its constituents. So then our objective. Oh, and then the other important thing I want to say. So there's this thing. This is going to. The reason we're doing this is for two reasons. One, it allows us to simplify that expression. The other reason is it allows us to use Stirling's approximation, which allows us to deal with the factorials in a way that allows us to use a sort of analytical framework. Okay, so Stirling's approximation tells you that the natural log of n factorial is equal to n times natural log of n minus n. Okay, and then to give you an idea of how, and this is not equal, rather this is approximately equal, but this approaches this for large n. Okay, and the n does not have to be that large. For n equal to 100, your error is already 0.89%. Okay, so in rest assured, the numbers that we'll be dealing with here are much larger than 100. Okay, so this is a very, very good approximation for the regime that we're working in. So and then so like we would have these components of the function that look like this, and there's you don't know how to differentiate that, right? But now you have something that you can differentiate, and there's some hand waving going on here because we're taking something that's discrete and we're going to be differentiating as if it's a continuous object. But the reason that's okay is simply because the n's are so large and the energy states are so closely spaced, and you're just enormous that it's a very good approximation. Okay, that's really without trying to get too much in the weeds. That's the best explanation I can give you. So that's why we can use it. Okay, let's see, we have enough room here. So I think let's begin with the fermions. Okay, so like I said, the objective we'll have in the end is going to be a sum over the natural log of W, Cj, and J. So let's just look at each of those terms for a specific J. Okay, so for fermions, we'll look at natural log of W, Cj, and J, Fermi graph. Okay. And then this is just the natural log of Cj factorial over Cj factorial, Cj minus Nj factorial of it's like here you have a product in here, so you can split that up into different terms. And then I'm going to split it up and apply Stirling's formula at the same time, and you'll be able to see this fairly easily. So this is like Cj and ln of Cj minus Cj. Okay, so that's like this term here. Minus Nj, natural log of Nj, plus Nj. So you're finding minus sign because it's on the bottom of the quotient. And minus Cj minus Nj, natural log of Cj minus Nj, plus Cj minus Nj. Okay, so all these constant terms that are hanging out on the outside get canceled. Okay, and then we can group like terms with Cj out front and the Nj out front, and we end up with, and I'm gonna pull out a minus Cj, and the reason for that is because it'll allow us to compare more favorably with the Bose-Einstein expression in the end. And you'll see why basically. But so we have Cj minus Cj times minus natural log of Cj, and then we pull out the minus Cj from here, and plus natural log of Cj minus Nj, that quantity, and then we pull out a positive Nj for the other group of terms. The natural log of Cj minus Nj minus natural log of Nj. Okay? And then now we'll recombine these inside into a quotient. Just continuing to use our rules for logarithms here. So this is the same as the natural log of 1 minus Nj over Cj. Okay, so this quantity over Cj. Okay, plus Nj times the natural log of Cj over Nj minus 1. Okay, so this is a nice simple formula, analytical formula, that we have for the natural log of WCJ Nj for Fermi using Fermi Dirac synthetsis. So then we'll do Bose-Einstein next. Okay, and then we'll do the same thing for bosons. So I think I'll skip here. I'll write down actually we have the formula right there. So we're going to take the natural log of that. I'm going to apply Stirling and gather terms in one step. This is something that you guys should be able to do on your own rather easily if you want to fill in the blanks yourself. So we're going to say it's Nj times the natural log of Nj plus Cj minus 1 minus natural log of Nj plus Cj times natural log of Nj plus Cj minus 1 minus natural log of Cj minus 1 plus this natural log hanging out here by itself, which is Cj minus 1 over Nj plus Cj minus 1. Okay, and then at this point, we note that in most of the situations we're interested in, we're going to have a high enough temperature such that Cj is going to be very large. Okay, so that at high temperatures, the energy states in each of those bins become extremely tightly packed, so that the Cj within an energy bin, it becomes very large. So if you compare it to any of these, to just one, Cj minus 1, like Cj plus or minus 1 is basically equal to Cj. Okay, so then we get rid of all of these minus ones here. They're not important. Okay. And so now we can group things into quotients like we did before. We have Nj times the natural log of 1 plus Cj over Nj. And you can see like this is looking very similar to that one. Okay. And then we also have plus Cj natural log of Nj over Cj plus 1. And then we also have this other natural log hanging out on the outside here. And then this is, in fact, let's pull out a minus 1. Okay, and it'll flip this. So then you have Nj over Cj plus 1. Okay, so now you see this is the same. So then you're gonna, when you group these terms, you're just gonna have a Cj minus 1 times this natural log, and then Cj is very large compared to 1. So this just ignore that term, right? So then now we can see we have this expression and this expression. They're very similar. They only differ by some pluses and minuses. Okay. So if we write down our objective in the Lagrange multiplier setup f of xi, let's put a line here because we're moving on to the actual optimization procedure. So our objective, f of, or just call it f, which is equal to the w of nj, natural log of w nj, okay, which is equal to the sum over the energy bins times the natural log of w cj nj, okay, is equal to the sum over all the j's of this quantity plus or minus Cj natural log of 1 plus or minus Nj over Cj plus Nj natural log of Cj over Nj plus or minus 1. Okay? And then the plus corresponds to Bose-Einstein statistics, and the minus corresponds to Fermi-Dirac. Okay, so this is our objective, and then the Lagrange multiplier setup. Now, what are our constraints? For the constraints, we'll just use like a total energy and a total number of particles constraint. Okay, as a function of all the NJs. So one constraint will look like this. So we'll just do this constraint. One constraint will have n minus the sum over j of the nj's is equal to 0. So just if you sum up all the particles over all energy bins, you just get the total number of particles. And then the total energy. Okay. And then this is where that assumption, so we have epsilon j and j equals 0. Okay. And this is where this assumption that the states are very tightly packed in these very small energy groups is important, because we're essentially assuming that each of the particles within that energy group have the same energy, epsilon j. Okay. Which on average will be true if the states are sort of like very, very densely packed. Their average energy is around that value. So if you sum them up, you should get this constraint. But just keep in mind that's what's going on here. Okay, so I'll just write out our objective function real quick, just to make it clear. We have sum over j of plus or minus dj, just reproducing what's above there, 1 plus or minus nj over cj plus nj natural log of cj over nj plus or minus 1. Okay, that sum. And then we also have plus alpha, we'll use alpha for this Lagrange multiplier, times n minus the sum over j of nj plus beta times e minus the sum over j of epsilon j and j. Okay, this is our objective function. And so we now want to take the gradient of this thing. All right? minus Cj times this quantity, 1 over 1 plus or minus Nj over Cj times chain rule plus or minus 1 over Cj. Okay, that's the first term. Second term, product rule, and natural log of Cj over Nj plus or minus 1 plus Nj times the quantity 1 over Cj over Nj plus or minus 1 times the quantity minus Cj over Nj squared. Okay, just differentiation. We've seen this before. And then we're differentiating with respect to a single Nj in this sum. So we just pull out an alpha, negative alpha, plus beta epsilon j. And then we set this equal to 0. Okay? And when we set that equal to 0, we're then acknowledging that we're solving for an optimal Nj now. So we'll put an Nj star in all these equations here going forward. We can see a lot of this cancels right away. These two things cancel. This Nj out front cancels. Okay? And then we see also that if we take this quantity and we pull it in here, okay, you cancel the first term, and then the other term it just flips. You take this, you flip this thing, you do this. So this whole like thing is just like 1 over, sorry, a negative because there's a minus sign here. 1 over 1 plus or minus Nj over Cj. Okay, so then now that cancels with this. You have the minus sign up front, so this cancels here, and what you're left with is just this. And the Lagrange multipliers out on the right side of the equation. Cj over Nj star plus or minus 1 minus alpha plus beta epsilon j equal to 0. Okay? And so we can solve this for Nj over Cj. We move that to the other side of the equation. We exponentiate. We subtract. This plus or minus is going to flip. Okay? We subtract or add, and then we invert to get the optimal distribution in the following way. Say Nj star over Cj is equal to 1 over x of minus alpha minus beta epsilon. Sorry, not minus here. It's just plus. We'll flip that later. Minus plus 1. Okay, so there's a sign flip here. When you move this over to the side, you exponentiate it, and then for the plus, you subtracted 1, for the minus, you added 1. So there's a sign flip here. So now minus in this equation corresponds to Bose-Einstein sign. Okay, and the plus corresponds to Fermi-Dirac. Okay, and this is our optimal distribution. All right, we'll frame it. Hang it up. I had a professor at Oregon State who would do that. And like when an equation was really, really important, he would like draw a beautiful, nice frame around it. And he'd like frame it like it was like a work of art. Anyway, this is my homage to David Lutzon. Okay. Now if you were doing like Lagrange multipliers normally, you'd have this expression, and then you would plug this expression back into the constraints over there, and then solve for alpha and beta using those equations. But since alpha and beta are wrapped up in this weird function, like a sort of a transcendental type of situation, you can't really solve them analytically. Give a sum over all these epsilon j's and whatnot, and so we can't really quite just put them back into the constraints and solve right away. Okay. So what we're going to do is we're going to focus on the case where the temperature is sufficiently high such that the particles are distributed widely across the energy states. So like what I mean by this is like the energy distribution is fat, okay? Which is like, which is kind of true in general. So imagine you have an energy distribution as the function of E. It's like something like this. It's like really filled out. So like your temperature, which tells you how fat this thing is high, okay? And what that means in practice is that your NJ, your occupation, your number of particles in bin J is much, much less than CJ. Okay? And we call this the Boltzmann limit. Okay, so that means that this number out front here is really small, right? So what has to be true about this exponential function if this whole thing is small, right? It needs to be what? Yeah, it needs to be really, really big. So if the exponential of alpha plus beta epsilon is huge, then this plus or minus 1 doesn't matter. It just effectively drops out. So in the Boltzmann limit, our distribution just collapses to, it doesn't matter whether it's fermions or bosons, it becomes irrelevant. You just have x of minus alpha minus beta epsilon. Okay? So whether it's bosons or fermions, it's irrelevant. So really, the only time you need to be paying attention to different types of particle statistics is when your temperature is really low, and then this distribution becomes very fat. Okay, or sorry, fat, very, very skinny. And so the occupation of a certain energy group might become high, and then this plus or minus 1 becomes important. Okay, but for our purposes, this is really what will be applicable. Okay, and now with this expression, we can actually determine alpha. So if we substitute this into that constraint right there, we have n minus the sum over j of Cj x of minus alpha minus beta epsilon j is equal to 0. Okay, and then this alpha does not depend on the j at all, so we can pull it out of the sum. And then we can equate e to the minus alpha with this function here, which is n over the sum over j of Cj x of minus beta alpha epsilon j. Okay? And then those of you who have taken a course in thermodynamics and physics, you recognize that this is the partition function, Q. Okay, how many of you guys have seen the partition function before? 1, 2, few, okay, like five or six of you. Okay, so this is the partition function. This quantity is going to be very important. Okay, this, like a lot of our thermodynamic quantities, pressure, entropy, we're going to be able to write it in terms of this thing. Okay, and we'll be able to construct this thing knowing what kinds of energy states are available in the system. So we can actually, because we know what the form, we're going to find what beta is later. But we know what the epsilon j's look like depending on our model. If we have translational energy states, we know we could fill those in and we can literally write down what the partition function is. Go ahead.
Are you saying that Q is the whole fraction or just the denominator?
Just the denominator, yeah. Okay. It's just the sum over j of Cj x of minus beta epsilon j. Okay. I'll frame this one too. This is an important equation. Okay. All right. And the reason we call it the partition function is because it tells you how the particles are partitioned in the system, how they're split up across the different energy levels. So if we take this e to the alpha and we substitute it into here, we can rewrite this distribution in the following way. We can say like nj over n, so the proportion of the particles, of the total number of particles that are in energy group j, is equal to Cj x of minus beta epsilon j over the sum over all j of Cj x of minus beta epsilon j. Okay, so you can see you just took the jth term out of this sum, and then you took the quotient like that. So it's like it's telling you what proportion of the particles are in the jth level. In fact, if you were to like look at, if you wanted the ratio of the number of particles between j and I, it would be the ratio between the terms in the partition function sum, right? Because the partition function denominator is going to drop out when you do that quotient. You're just going to take the ratio of the terms that correspond to that energy group in the partition function. So that's why we call it the partition function. It's because it's telling you how the particles are partitioned amongst the different energy levels. All right. So you can start to see why it's so important. Okay, and we'll find beta later. So we know what alpha is in terms of beta right now, and we'll determine beta later when we actually relate all of this back to thermodynamic quantities that we're familiar with, and we'll be able to solve for it. Okay. So now we're going to talk about occupation number, and this is where there's like some this will be like the last thing we talk about today, because then it'll be nice. The next lecture we'll start talking about entropy. So the occupation number is this object that in the book. It's not necessarily it's not an essential idea, but the first thing that we'll observe is that this nj over cj, so this is the number of particles in energy group J, this is the number of states available in energy group J. So in that energy bin J, we have that this is essentially giving you like the average number of particles in each state, right, if you smear them out, okay? So that's the average number of particles in each state. We're going to call that the occupation number. And then the other thing is we're going to, instead of summing over the energy bins, or the energy groups, we can instead just sum over the individual energy states. And let's say that we're summing over I in this case. So instead of going from, it's not on the board anymore, but instead of going from over these bins in energy, let's instead stop at every single state along the way and do it that way, okay? And so in that case, the partition function changes. It's just, you're now just summing over every state, so you don't need to multiply by Cj at every step. It's just the sum over I, x of minus beta, epsilon I, okay? So there's no number of states, you're just summing at each individual point, okay? So you can recover this from here by first acknowledging that within an energy group, all of these energies, so like each of these epsilon i's, they're all essentially equal to this epsilon j of the group. So if we make because the energy spacing is so small, we're saying that all these individual energies, epsilon I, is roughly equal to epsilon j, okay, of the group. And we're summing over the energies in the group. So if we acknowledge that this is basically true, then you can recover this partition function from this one, right? Because you're just going to have Cj terms as you sum over the groups that are exactly the same, because all the epsilon i's are the same, and then you can group them like that. Okay. So that's transitioning in our thinking to summing over individual energy states from summing over energy bins. And then now we'll just define this equation. Just like baffles me, but we're going to define this thing called the occupation number Ni as Nj over Cj. Okay, so this equation is a bit confusing because you got all j's on this side and all i's on this side. But the important thing to think about is like, what does this mean in words? It means the average occupation of the energy states within bin J. Okay, so what Ni is it's giving you the average occupation of energy state I, because there's all these different energy states within here. They all have average occupation Nj over Cj. So you're then going to say that the average occupation of any specific energy state is just equal to Nj over Cj. And then we'll recast this expression on the right side in terms of just epsilon I. because we've like we said, these are basically the same. So this allows us to write Ni as just n times e to the minus beta epsilon I over sum over I e to the minus beta I. Okay, so it's like a simpler expression. But this is the same, if you took the CJ over here, you move the n over here. These are the same expressions, because we've said that epsilon j is the same as epsilon I, and we've showed that the partition function can be expressed as a sum over the individual energy states. Yeah?
So in the Boltzmann limit we have Nj is way less than Cj. So we'll always have Ni is way less than 1.
That's true. That is true. So so the Ni, so what this is it's the average occupation of a specific energy state. So there's the probability that you're going to find a particle in a single energy state and a very specific energy state is almost nil, right? Like because there's so many energy states. There's way more available states than there are particles. Way more available states than there are particles. Okay, so it is consistent that Ni is very, very small, like much, much less than 1. But what it gives you is it gives you a distribution over the energy state specifically, right? So now our distribution is more granular. Before we were looking at a distribution over energy bins. Now we're looking at a distribution over the individual states. Okay? No problem. And then the other thing, and this is the last thing I'll say. So we can also note that a lot of the energy states are degenerate. We're going to see this and we've already seen it actually. We talked about, when we first started talking about the CJs, we were talking about individual energy levels and degenerate energy levels and translational energy, right? These quantum numbers, that was like a sum of squares, and you could like permute the different quantum numbers that correspond to each direction. And those are the degenerate energy levels. And so we can also choose to sum over the energy levels instead of the energy states. And then in that case, we can denote that by like a lowercase l. We can write this as NL is equal to N times GL, where GL is the degeneracy of the energy level L, e to the minus beta epsilon L, over the sum over L times GL, or sum over L of GL e to the minus beta L epsilon L. Sorry, at one point I just switched to E's instead of X, but I think you guys get the idea. So this is the same. This is the same idea. So now each energy level L, those are all the states which have the exact same energy, like degenerate energy level states. And then this is actually like the form of the partition function that, at least in physics, and I think even in this class, this is the form that you're going to like work with most often. Okay, it's like you're going to be summing over each energy level. Okay. All right, so that's about, we're right at time, like 10:20, and that's a perfect place to stop because we'll in the next class we're going to immediately start talking about entropy. So is there any questions, by the way? Anybody have anything that wasn't totally clear? All good? Okay, come to office hours at 11:30 if you have any questions. I really wanted to do this, I just knew I wouldn't have time. But I have, if you guys haven't ever seen an explanation of how Lagrange multipliers works, that method, I can give you a nice, like draw some pictures and give you a nice explanation as to why that method works. Because a lot of people are just given it as a description. What's up?
Would you mind posting the lecture notes?
Yeah, I can scan them.